Good morning, everyone. Today we have lecture 11 of computer vision, which is optical flow and tracking. Optical flow and tracking is, yes, again, one of the important topics of computer vision, and why it is required. Because if, let's say, camera is moving, we want to calculate that camera movement from frame to frame. And let's say if camera is not moving and your scene is moving, some objects in your scene are moving, again you want to estimate their displacement in the scene, and that's again is from frame to frame because you have a video sequence in your optical flow. So we'll look into optical flow, we'll discuss the motion field, we'll discuss tracking and some applications of optical flow. Optical flow constraints, and we'll discuss few techniques, optical flow techniques, which include Lucas Kanade tracking and mean shift algorithms. These two main famous algorithms of optical flow. So, what happens when a camera moves? So imagine a moving video camera. There will be a relative motion between the camera and the scene. So motion is always relative, right? So if one object is static, the other one is moving, you say, okay, that's with reference to this particular object. So motion is always relative. And we'll keep that thing in our mind while calculating optical flow. So this motion will appear as displacement of pixel in consecutive images. So consecutive images in this case will be different video frames. Each frame is treated as an image, right? So this motion will appear as displacement of pixels in consecutive frames. If the motion is small between consecutive images, the displacement of pixels will be small. What is the acquisition speed of most of the cameras these days? 25 frames per second, right? And you have, of course, you have some cameras with really high frame rate, but 25 frames per second is the normal speed for common cameras. So that means how much will be the difference between one frame to the other frame in terms of time? 25th of a second, so that's 1/25, which is very, very small. So motion in this small amount of time would be minimal, right? Because 1/25 is a very small time, so motion will be very minimal in that time. So if the motion is small between consecutive images, the displacement of pixel will be small, of course, right? So motion field. Let's say we have two different images. One image was captured at time t, another one has been captured at time t plus 1. So before discussing this right-hand image, I would go to the definition first. So what is motion field? Projection of 3D relative velocity vectors onto the image plane. So motion field is the projection of 3D relative velocity vectors onto the image plane. And this right image is showing those vectors. This is the actual value that you get from your real world. As you move your camera, right? If your camera is moving or some of the objects are moving, you actually get the velocity vectors. And when you project those velocity vectors onto an image plane, that's called motion field. So if you look at this image, you have some velocity vectors pointing in different directions. There are some dots as well, which indicates that velocity vectors are either pointing towards the image or outwards, right? So this displacement field basically represents your motion field, and that's actual in your 3D, in your real world information. Now, what is optical flow or optic flow? Observe 2D displacement of pixels, brightness patterns in the image. So optical flow is your calculation in your image plane. All the calculations that you do in the image plane that fall in the category of your optic flow. So all real world stuff that deals with your velocity vectors. Velocity vectors, again, that's related to the movement of the camera. It's called motion field, and optical flow is your observed 2D displacement of pixels in the image. Now, most of the time, motion field is what we want to find, but optic flow is what we actually measure from the images, because the information that we have is the video sequence, right? So we, let's say, define one point as a reference in the first frame, and then we track that point, right, throughout that video sequence. So optic flow is actually calculated in our daily lives, in our actual computer vision research, but most of the time motion field is what we are actually interested in, what we are after. Now, to explain some difference between this optic flow and motion field stuff. So I hope you guys must have seen barber's pole, either video in some, maybe in some circus or somewhere in some carnivals, right? So as this barber pole spins, what sort of, how does it look like? It appears that these black stripes are moving upwards, right? So that upward motion is basically your optical flow, right? When the actual motion, which is spinning around z-axis, is your motion field, right? So that's your actual motion in real world, and optical flow is what you get. So even your eyes, we have the best visual and recognition system in the world, right? Still we think, okay, these stripes are actually moving upwards. So that's basically optic flow. And yes, even with your any of the state-of-the-art computer vision algorithm would do exactly the same, right? Now, this leads to a problem called aperture problem. So we can only measure the component of optic flow in the direction of intensity gradients. So if you look at barber's pole, what will be the direction of intensity gradients? One of the stripes is shown here. And this barber's pole is moving in that direction, in that particular direction. And if you compute the gradients, they will point upwards. And we cannot measure the component that is tangent to the intensity gradient. Which one is the tangent component? A is a tangent component. You can't measure we cannot measure the component that is tangent to the intensity. You can't measure that particular component. Even any state-of-the-art computer vision algorithm can't measure that, right? Now, to give you some intuitive explanation of that, let me just quickly go through some of the images. Let's say in your MATLAB, you compute this sort of matrix, right? This is somewhat similar to your barber's pole pattern, right? You have white and black, so you can create this matrix. So let's say it's a 100 by 100 matrix. You have 50 rows comprising of all the white pixels, 1 values, and 50 rows comprising of all the 0 values. Now the next thing is you compute gradient, and you plot all the gradient values on top of this image, right? So these blue, can you see the difference? These blue arrows are actually your gradient values. And if you just zoom into this image, you will see these sort of arrows pointing from black to white. These are your gradient values. And as I was telling, you compute your optical flow in the direction of the gradients. So your gradient is always from when there is an intensity change. So that's how your gradient would look like. And let's say if you move to the white region or the black region, the gradient values are very small, almost 0. And I was telling you the tangent component is very difficult to measure because that's along the, because intensity value is same in that direction, right? So when you have a change in intensity, you can compute gradient. In the case of barber's pole, that's your optical flow is along the gradient direction, and that's the reason. And if you want to implement in MATLAB, these are just 2 lines of statements that you can use to compute. And A in this case is again a matrix, 100 by 100 binary matrix. Okay, going back to the lecture. So any questions so far? Okay, so the optical flow constraint. The intensity at a point in an image is a function of its position and time, that is I, X, Y, T. To derive the optical flow constraint, we are concerned with its spatiotemporal variation. So what is that spatiotemporal variation? So in this particular case, what will be the spatiotemporal variation? The gradient values, because gradient values are changing in this particular case. And what is this IXYT? That's spatiotemporal value at one particular pixel at a given time t, right? So IXYT is the value and variations will be the gradient values. Now to see how I changes after a small change in time and position, we look at its Taylor expansion. So in the next frame we say, okay, after time, some given amount of time t plus dt, there is a change. We move to the next frame and we compute that change, and that's given by this Taylor series expansion. And of course we look at the first order derivatives in this particular case, and all the E terms are the higher order stuff, and we are just ignoring that for this computation. So if the motion of a point is very small, then the illumination function for that point should not change. That is, the brightness of a point in its new position at time t plus dt should not change. So what did we previously say? How much is the time difference between the two frames? 25th of a second, 1/25. So in that small amount of time, change is very minimal. So let's say if your pixel has, or the object has slightly moved, the neighborhood has not changed significantly in that small amount of time. And even let's say if you're tracking an object, the brightness of the object itself stays the same, right? If you're tracking a pixel on an object from one frame to the next frame, there won't be a big change there. So that brightness of the object would stay the same. So this change of intensity value is very small. And so the intensity value does not change. That means your left-hand expression is value is equal to the intensity, like the intensity value in your time t and intensity value in your time t plus dt is exactly the same, right? So when you substitute this into your actual equation, what do you get? You get curly I of curly x dx plus all that equation equal to 0, because these two terms are equal actually, right? So there is no change in the intensity value. So if these two terms are equal, you just shift this one on the left hand side, it will make it 0, right? So this whole equation becomes equal to 0 here in this case. And this expression can be written as I of x u plus I of y v plus I t equal to 0. I of x is your, what are these derivative terms, these partial derivative terms? The gradient values, right? These are the gradient values, right? What is u and v? We'll calculate them in the next few slides, and we'll see what are these values. So uv are the x and y components of the velocity term that we are after, right? So u and v want to calculate in this equation, and this ixu plus iyv plus it is a very important optical flow equation, and almost everything related to optical flow is grounded on this particular equation, and this is called optical flow constraint equation. Any questions on that slide, on this particular slide? Right, so intensity values from one frame to the next frame, or at time t and time t plus dt are exactly the same. So we say, okay, as the intensity values are 0, this equation becomes equal to 0, and we just substitute ixu for the variables of the equation, and this equation itself is called optical flow constraint equation. Now, okay, so this equation can be written in the matrix form. With little manipulation, you can write it in the matrix form, and with little more shifting and manipulation, you'll get this particular equation. If you look at this, you'll see that vector uv, the vector that consists of uv and the vector that consists of ix and iy are the same, but there is just a little displacement here, which is represented by this particular expression, right? This is just a value, right? The gradient values of x, y, and t, right? And you already know these values from your image plane, from two different planes. You can compute that from your image plane, from two different images. So the two vectors on the left are the same. The only difference is they are slightly displaced, right? The one on the left hand side is slightly displaced by the factor which is given here with the negative sign. So the velocity that we can estimate is in the direction of the intensity gradients. As I've told you, Ix and Iy are the intensity gradients, right? Ix and Iy are the derivatives in the direction of x and y. They are the gradients. So the velocity that we can estimate is in the direction of intensity gradient, and this confirms the aperture problem that we raised earlier. Now coming back to that optical flow constraint equation. So Ix, Iy and It are the known variables in this case, while u and v are the unknown variables. Now Ix and Iy, if you remember that image that I've just showed you a few minutes ago, you can calculate your gradient using that values for two different images, right? So you know your Ix, Iy using that particular method that it is displayed, and then with It, it's a time difference from one frame to the next frame. You can just subtract that to get your time value. So Ix, Iy, It are the known variables, while u and v are the unknown variables, and we are trying to calculate these two variables. Now if you look at this equation, this expression, the optical flow constraint equation, is in the form of a equation of a line, right? So Ax plus By plus C equal to 0. It's exactly the same. So optical flow is actually along a line, right? So optical flow calculation is along a line. So this optical flow is constrained to be on a line. There are two unknowns and one equation per pixel. So if you have two unknowns and one equation, can you solve that equation? No, you can't solve that equation. The only possible solution is you can determine only one direction in that case. If you have two unknowns and one equation, you can only solve for one direction. And that again gives you an aperture problem. That again leads to the aperture problem, right? So you substitute one of the values equal to 0 and solve for the other one. So you can calculate for one direction if you have one equation and two unknown variables. Now, so we'll look into some of the techniques, and some of the authors have tried to solve this equation, and those techniques will help us to understand like how to get the values of u and v. So now we have different methods of calculating optical flow. One is differential. We have differential techniques where we have dense flow based on spatial and temporal variations of the image brightness at all pixels are used to calculate the optical flow. And in the second case, it's a matching technique. It's like a sparse flow. Only some reliable pixel values are used. So you find you detect your features, and then you track those features. You match those features and track the object to accomplish optic flow process. Now, one of the famous technique is Lucas-Kanade motion technique, and this is one of the famous optical flow methods that have been proposed so far. So, but the thing is, this method needs two or more pixels to solve for both variables, right? Both variables u and v. You need two or more pixels. So, if we go back to this equation, it says there are two unknowns and one equation per pixel. So this equation is for one pixel. If you have two or more pixels, that means you will have multiple equations, right? So having multiple equations and two unknown variables, you can easily solve them. Okay, include pixels with different gradient directions to solve the aperture problem. Now, if you look at this image on the left, you have a pixel, and let's say this frame is moving in the direction of this yellow, or I think it's yellow or orange or brown arrow, right? It's moving in the direction of this arrow. I think it's yellow arrow. So what your visual system will perceive, you feel like this pixel is moving to the right, right? If you have just one direction, one pixel, and if the frame is moving in this direction, or the image is moving in this direction, you will perceive it as if it's moving on the right. Similarly, for this particular case, you will, like your visual system will process that as if this pixel is moving in the upward direction, right? Now, if we have two or more gradients, we can find the right solution in this particular case, right? So the right solution, if you have two more pixels, and if this is moving in this direction, you solve for these two pixels, this will be your final direction, which is exactly in the direction of this arrow, right? Which is actual direction of, or the direction of motion. Okay, so we have one equation and we have two unknown variables. So to solve this equation, we impose some additional constraints on optical flow. So optical flow is locally smooth, that is pixels in a small neighborhood have the same displacement. So instead of restricting this problem to one pixel only, you take a neighborhood of pixels, right? Let's say you take 5 by 5 neighborhood. So you will have 25 pixels there. And 25 pixels mean 25 different equations, because we have this equation at 1 pixel, right? So to solve this equation, you take one neighborhood, a fixed size. You can use 3 times 3, 5 times 5, 7 times 7, right? So we just say we take a window of 5 times 5, which gives us 25 equations, because we have 25 pixels, and this equation is for 1 pixel, right? So we have 25 different equations. Now with 25 different equations and two unknown variables, can we solve it easily? Of course we can. We have no more number of equations than the unknowns, right? Now, now writing these variables in the form of a matrix, you have all the gradient values on your left, which becomes your matrix is a 25 times 2 matrix, because you have 25 equations, right? 25 rows and 2 variables, 2 gradient values for each pixel. Then you have unknowns, which is given by matrix Z, which are 2 times 1 matrix. And then you have another matrix B, which comprises of your time gradients, right? The same expression that we did in the previous slides, the same expression. Which is again a 25 by 1 matrix. Now if you look at these two matrices, their dimension is same, because if you multiply a 25 by 2 matrix with a 2 by 1 matrix, you will get a 25 by 1 matrix in the end, right? So this relationship holds in this particular case. Now, our ultimate aim is to minimize AD minus B square in this particular case. Now starting with our left hand side equation, AD equal to B, you just multiply both hand sides by A transpose. So this is a method actually adopted by Lucas Kanade, okay? And you can find more details in the paper as well. So you multiply both sides of the equation by A transpose, and if you rewrite this equation in the matrix form, you will get this sort of expression. So all your I values here, you have some I square, X square terms in the expression as well. That's just a matrix representation of the equation. Now to solve for this equation, what do? We are interested in U and V. So this matrix A, you will shift it here on the right hand side, right? This will become A inverse, right? A transpose A inverse. So to solve this equation, there are some requirements. When is this solved here? When A transpose A is invertible. So that's very important, it should be invertible. That's not the case every time, especially when you have a singular matrix. MATLAB will give you an error, right? So, do you know there's another built-in function? Of course, you take I and V inverse. If let's say if you get error in MATLAB, you know any other function to use? That's mostly for singular matrices, when the inverse of a matrix is not possible. So for such cases, there is another function PINV, right? So you can use that function directly. Right? It's again based on a slightly different method for computing the inverse of a matrix. So when is this solvable? When A transpose A is invertible, the eigenvalues of A transpose A are large. The ratio between the eigenvalue is not too large. I'll come to the eigenvalues in the next few slides, right? So just keep in mind this equation is solvable when these three conditions are met. Now, when was the last time we discussed this equation? Are you guys familiar with this equation? Any guesses? Harris corner detector, right? So last time we discussed this equation in our feature detection and extraction lecture, right? So just a quick revision of Harris corner detector before we proceed with the that matrix. So Harris corner detector mathematically determines these three cases. So for a flat surface, no gradients. For an edge, we have gradient in one particular direction, and then for a corner, we have changes in all directions. So we have two different gradients in that particular case. That's how the corner is detected by. That's how Harris detected the corners in his technique. Now, if you also remember, eigenvalues are large at the corner. That's what we also discussed. So eigenvalues are large at the corner. If one eigenvalue is larger than the other eigenvalue, that's an H, right? And then for flat surface, we have very, very small eigenvalues, almost equal to 0. And this was the equation that we discussed in one of the previous lectures. So in that particular case, EUV was special shift in single image. Now it is displacement across two different frames in time, right? IXY is the intensity value for the previous frame, while IX plus U and Y plus V is the intensity value in the current frame or the shifted frame, and W is your window function, the window function that you chose. So in our case, it is a 5 times 5 window, right? But again, you can choose a smaller window like 3 times 3. So corners are a region with two dominant gradient directions. Both lambda 1, lambda 2 are big, so both eigenvalues are large. Lucas Kanade works best when lambda 1 and lambda 2 are big. So Lucas Kanade technique works best at corners. So no aperture problem at corners. Why? There is no aperture problem at corners. Why? So when do we have an aperture problem? When we have just one direction of the gradient, one motion direction, right? So when we have just one direction of the gradient, we call it an aperture problem, right? One direction of motion. So no aperture problem at corners. Why? Because it says corners are regions with dominant gradient directions. We have different gradient directions in that particular case, at least two gradients, right? So we can easily find the direction, the actual direction of motion or the optical flow. The corners are good features to compute optical flow. So as we have said that Lucas Kanade optical flow technique uses corners. So it will only find optical flow at certain points. So these points are the corners. Sometimes we need to find optical flow at all pixels, and for that we have another. So you find what happens in Lucas Kanade, you find one corner point, you compute the gradient values, and you keep on tracking those pixel values. So it's just restricted to one particular pixel point, right? Detection of corners, and then it follows that. And we will cover one algorithm for dense optical flow in this lecture, which is Farnabach's two-frame optical flow. So before going to that lecture, I have just a quick video to share with you guys. It's based on optical flow using Lucas Kanade technique. And if you look at that, the tracking is really good in this particular. This is all based on optical flow. So if you see as the cars are moving, you have fixed background. The gradient value, computation of gradient value is pretty easy in this particular case, right? So they normally assume some ideal conditions like this, where we have some static sort of background that doesn't change, and then some moving objects, and that's how it actually works. Okay, mean shift, we'll come back to this one later. Now, Farnbach's two-frame optical flow is based on polynomial expansion of a neighborhood of pixels. Again, it considers multiple pixels, so it considers a neighborhood of a pixel, and each pixel is approximated by a polynomial of this type, which is given by f1 of x. And what is the order of this polynomial? What is the order of this polynomial? Two, because it's x square, ax square plus bx plus c, right? And what is x here? X is a value or a vector that has multiple values in it. What is x in this case? So we said neighborhood of pixels. So when you say neighborhood of pixels, we have multiple points, multiple pixels. So x is a vector in this particular case. So if you are using a 5 times 5 pixels, 5 times 5 windows, x will be a 5-dimensional vector, right? So you construct a new signal f2 by global displacement. So you take that neighborhood to a new location in the new frame, in the next frame, right? Or in the next image. And you compute that polynomial again for that displacement d in the new image. And with little bit solution, with little bit manipulation of these expressions, you bring all the x squared terms on the left, then the next is your x terms, and then all your constant values, right? And if you rewrite this equation in the polynomial form, you'll get x transpose a2x plus b2 transpose x plus c2, which again is the polynomial form of the equation. So we are not interested in these higher order terms or these constant terms. We just substitute them with c2. And with this substitution, we have a2 equal to a1. That means exactly the same as we have in our previous frame. It didn't change. But b2 is equal to b1 minus 2 times a1d. Now, if you go for a solution, which equation is important? b2, because we have that factor d in it, which is the displacement we are trying to compute, right? So we are interested in calculating the displacement. If you remember from the initial discussion on optical flow, definition of the optical flow, what was that? Calculating 2D displacement in the image. That d represents that displacement, okay? So you take a neighborhood in one frame, you shift that neighborhood by a factor d, you displace that, and d is of course your displacement, and you solve that polynomial equations. In the end, you just rewrite the equation in the polynomial form, the second one, the new signal f2, and substitute those values and look at the variables. So b2 equal to b1 minus 2a1 times d is our equation of interest, and we will be solving this equation. So now this is our key observation, and when we calculate the value of the displacement, that is optical flow from this, just again a little bit manipulation of variable, you shift the variables, you get d equal to minus 1 over 2 a1 inverse b2 minus b1. If you look at these this particular expression, these are just the coefficients of x square and x, right? And again, this equation is solvable if A is non-singular, because for a singular matrix you can't compute the inverse, right? So it should be non-singular. Now coming to tracking. Now using optical flow, we can track pixels or corner over multiple frames. So keeping this displacement thing in mind, keeping Lucas-Kanade technique in mind, where you detect corners and then you track those corners throughout the video sequence, right? So using optical flow, we can track pixels or corners over multiple frames. Sometimes we don't want to track every pixel or every corner. So in that particular case, you go for a sparse technique. You go for some specific, some dominant pixels, right? So just keep the idea of that feature detection in your mind. So you have some repeatable features in every frame. You go for those features and you track those features. So let's say if you're tracking a car and you detect the corners of the car, you just keep on tracking those corners in all the images. Yeah. Uh, yes, that you can do. We have similar discussion on the color-based tracking in the last few slides, but yes, you can do that. So you can do that. You can just specify, let's say compute the histogram, a color histogram, or a gradient histogram for one frame, and do the same for the next one, and then you can compare the histograms. And the closest one will help you to identify the object in the next video frames, and you can easily track that. Again, yeah, with the PCA will be one of your feature, and yes, of course, you can then use that feature to track your object in that particular case. So,
how would the color histogram let you determine different features? Because I thought the color histogram just like tells you what the image looks like and compare it and say this is similar to another different image. Isn't that just a summary of the entire image, not like each object?
It's true. So it's for the. So we have actually we have one slide on that. We have one last slide on that. That will actually explain you. So if you remember, we also discussed this in feature extraction thing as well, where we had different histograms for different objects. Given a duck image, we had a histogram of the duck, and then we had a histogram of duck, a yellow, I think that was a aluminum foil or something, and there was some other object as well in the image. The histogram of the duck was like quite comparable with the original image, right? So of course the histogram has something to do with the color information plus the shape which is there in the image. So even if you rotate the shape, that would still remain the same. So we have one slide on this one where we'll compare the color information, the histogram information, and that I hope will help you to understand that stuff. So why tracking? We may want to track a specific object such as a tennis ball, right? During if we have some world championship going on, we just track the object ball just to make sure it's falling within the court and all that stuff. You can track pedestrians. You can track cars. The video that I show you, we were tracking different cars in that particular case, or even small or simple blobs. Blobs will be, let's say if you take log of something, it will give you a blob sort of information, and then you can track that blob. Or let's say if you Google or you go to YouTube and search for, let's say, satellite image tracking, right? So you'll see some tiny vehicles there, and they will appear like small blobs, like small blobs are moving there. So we can track all that stuff using the optical flow technique. Now, matching observation in a new frame to a set of track trajectory is what we do in the tracking. So we predict the next location or the next point on a given track. So when you say tracking, what are the assumptions? So let's say we have two different tracks, and we are trying to estimate the location of, and we have two different objects which are moving along these two different tracks, and we are trying to predict the next point along the two tracks. So number one, what is the assumption when we say tracking an object? The starting point is given already, right? You know the starting point, otherwise tracking is not possible. So you already know the starting point, you have some information about tracking, and let's say given 3 points along your track number 2, and you have to determine which one is the next track, and given 2 points along track number 1, you predict which one is your, you're just predicting, right? So which one will be the next track? So predict position along each track. You say, okay, one of these positions is possible, and you actual match should be close to the predicted position. Okay, that's again based on different computation of different distances between the points, plus the trend your path is following from here. So based on this trend, based on different distance values, you predict, okay, this point is the point where object is expected to land, let's say, right? And what happens in the tracking then? It's not like, okay, you predict this point, you predict this point, you predict this point, and you keep on going. No. What do you need to take care of? What is the next thing? So if you look at, so some of the matches, for number one, so you predict something, some of the matches are highly unlikely. So if you look at this trend, you don't want this object to certainly jump here, right? Similarly, same goes for this one. So you look at the previous pattern, right? And then you predict some values. And how does this tracking work? So you predict a value. You don't just keep on tracking an object. You predict a value. You wait for the object to get there, and then you match your predicted value with the actual value. If it's exactly the same, you keep that value. Otherwise, you update your values and you update your template. Let's say if you have a window, you update that template. And you do the same for the next patterns, right? And let's say if you're using some sort of neural networks, that will automatically learn these parameters, these values, and it will automatically there will be one point in time when it will automatically predict very accurate values, right? Now, coming to the Lucas-Kanade tracking technique. So we have a 5 by 5 window assume, but again, you can use any size of window, right? Instead of 5 by 5 window, we can choose a bigger window around the object. Let's say if you have a bigger object, you're tracking a big truck, you'll have a big window. And let's say we are just tracking a car in this particular case. So instead of 5 by 5 window, we can choose a bigger window around the object and track it with Lucas-Kanade approach. The problem, the appearance object can change over a few frames. How can the appearance of the object change from one frame to another? How would that change? How would the appearance change? Yes, slight shifting of the vehicle, illumination. So let's say you started on a sunny day and suddenly there are some clouds somewhere, illumination changes. Or you are tracking your car in the afternoon and let's say now it's getting evening, again change in illumination. So appearance of the object would change with the illumination, with little rotation and all that stuff, right? So appearance of the object can change, which is the main problem if you have a fixed size window. And then and to take care of these two things, what do we do? So one option is to update our template. What is your template? That window size. So you can say that's adaptive to that change actually. So if your vehicle is changing, you can increase the size of the window. And like if it's in this particular direction, you can keep the window smaller. But if you have, let's say, this sort of thing, or even slightly more rotated stuff, you can actually increase the size of the window. And the other thing is to introduce a fine warp into the equation of optical flow. That can also help you to tackle this problem of appearance changes, right? These things have been explained well in detail in the Lucas-Kanade paper, the paper that he proposed. And I have given link to that paper in what you need to know stuff in the lecture slides, right? So if you're really interested, please go through the lecture, that paper as well. And that will give you some more idea about this tracking and optical flow stuff that Lucas-Kanade has proposed in his paper. So any questions so far, guys? Any questions? Okay, what do we have here? Okay, so coming to another technique which is called tracking with mean shift. Now, in mean shift is done when for tracking objects whose appearance is defined by histograms. So here comes the histograms that we were discussing, right? So we had some questions on the histogram related. So for tracking objects whose appearance is defined by histograms, we use mean shift. And histograms, you can think of color histograms, gradient histograms, or any histograms, right? And the basic idea is to shift the center towards the mean of the data in feature space and shift the center of the object that you are tracking, right? So you shift the center of the object that you are tracking to the mean of the data in feature space. And center of the object, if you have a fixed size window around an object, you can get the center of that object, right? Or center of that particular window. Now, mean shift is a tool for finding modes in a set of data samples, manifesting an underlying probability density function in Rn dimension. And you can think of PDF in feature space, color space, or scale space, right? So we have next slide that will actually explain you how to, that will give you some intuitive explanation of this technique. So let's say you have your data points. The data points again will be your pixel data in this particular case. And you have non-parametric density estimation of this function. And if you compute your discrete PDF, it will appear something like this here. And if you have non-parametric density gradient estimation, you can get the peak of the data, which will be your mean value, right? And our ultimate aim is to get here, to bring center of the object or the center here, right here on the mean of the data. Now, intuitive description. So let's say we have this blue as our region of interest, and this tiny blue circle is the center of the object, and the orange one is our mean of the data. Now what happens, you compute the mean and you try to bring this center close to the our region of interest, center of the region of interest close to the mean. So you compute that, you bring it close to the mean, you compute your mean and your center again it's shifted slightly, you compute your mean again, and you keep on shifting that. So you'll see that, okay, with different iterations, your center of the object is getting close to the mean, and finally it will be exactly at the location of the mean of your data. That's how your mean shift, basically your mean shift, like the name of the technique itself is pretty much explaining everything. So you are trying to shift to the mean of your data. Now, okay. Now there are different ways to perform this mean shift. So mean shift and color models, there are two approaches. You create a color likelihood image with pixels weighted by similarity to the desired color, best for single colored objects. So you have object with one specific color, and when you have object with specific color, you try to shift, you have the information about that particular pixel or center of the object, you try to bring it close to the mean of the data for tracking purposes. And then another one is represent color distribution with a histogram and use mean shift to find region with most similar distribution of colors. So we'll discuss the first technique. So we'll use the color information when you have an object with one particular color information. So what happens in this particular case? Compute likelihood maps where the pixel values are proportional to the likelihood that the pixel comes from object we are tracking. So what will be the likelihood? So for object, any pixel on the object should be equal to 1, and all the other pixels should be equal to 0. And let's say if you are tracking a face, what will be the likelihood? The skin color, right? So you have clothes in different color, you have skin in one particular color, right? So that likelihood is the color of the skin in this particular case. So if you have you are able to find that likelihood, you represent that by 1 and all the other pixels by 0, right? And then once you have that information, so computation of likelihood can be based on your color, texture, shape, predicted location. So predicted location, one particular location in the image, and then you say, okay, in the next frame this location will be right here. Or you can use combination of all of them. And of course, if you're using combination of all of them, your tracking would be good. So you say color, take find texture, okay, take shape tick, predicted location tick. You say, okay, we have 4 different features to track an object, and all of them are giving us high score, right? You say, okay, that's good. We are actually, this is the object we are after, right? So just likelihood, just keep in mind, the area of likelihood will be all the 1 values and all of the 0 values. And again, as an example, if you're tracking the face, likelihood region will be the likelihood will be the skin color itself, right? Now the brightness of the pixel represents the likelihood that the pixel belongs to the object we are tracking. So if you're using, let's say, color information, or even if the grayscale information, that the color of the object itself will remain the same, right? So the brightness of the pixel represents the likelihood that the pixel belongs to the object we're tracking. Again, with the brightness you can think of the skin color as well. That doesn't change for a particular face. And if you perform a standard shift on these pixels, you will see that the windows, and notice how the search window moves towards the center of the brightness pixels. So you start your search here. The mean of your data is right here, right? So your mean of the data is somewhere over here. Center is somewhere over here because you have more brightness here. And let's say you define your region of interest here. It has a center somewhere here. You start to reduce the difference between the, you slowly and gradually start your mean shift, right? Process of mean shifting. So you shift the center of this window to the mean of the data, or the center of the data. So as I've explained to you, there are different steps. You compute the mean, you compute the center, you compute the difference, then you slowly and gradually move towards that center of the your data. Okay, so before we look into this technique, so I found this video which says mean shift tracking. So as we said, that mean shift tracking, we have objects with one specific color, and you'll find that they're tracking a person with this orange shirt, right? So this color information for this object is fixed. Now if you look at this person, the shirt, color of the shirt and shorts is fixed, right? You already know. Maybe they're trying to just fix it to the color of the short, which is black actually. Now again, the color of this ball is different from rest of the images. The brightness is staying the same. So with the mean shift, it's easily tracking the ball. Now if you look at the window, it's just, now again, yellow is quite prominent, right? And it's different from rest of the images, rest of the pixel intensities. And tracking is very good here in this case. Now tracking a car, again, the color of this car is quite different from the background, from other objects, and they're easily tracking that. And for such videos, what do they say? Don't try this at home, right? So just an example of mean shift tracking. So just keep that definition of brightness in your mind, right? And the likelihood is, in this case, is the color of the car itself, or the brightness of the car itself, right? So okay, that's all. I think we just stop here. Okay, so as an example, we'll also look at a technique called cam shift, which is continuously adaptive mean shift. It was written by Bratsky, and it was published in IEEE WSEV, Computer Vision Face Tracking. And in this particular case, the likelihood is skin color, right? So they take skin color as a likelihood, and they find the location of the face by mean shift. Again, brightness will stay the same in that particular region, right? In the face region, because of the skin color. They find the mean, and then they track the face. The size and roll found by fitting an ellipse to the points, and they track the face by fitting an ellipse. Instead of a rectangular window or a square window, they're using an ellipse. And the good thing about this cam shift is you can find the implementation of this technique in OpenCV. Have you guys used OpenCV? So you're familiar with OpenCV, that's good. So you'll find this technique in cam shift in OpenCV, and it's very easy to implement and install and execute, right? So ready to use sort of stuff. So just another example from okay, so that's an example of cam shift. And you can see there's an ellipse around the face, and even with the rotation of the face or shifting, the window is still staying there because likelihood, what are we following? The likelihood of skin color, right? And the brightness will be centered at the, so your center of, what do you call it, the mean data is right here, right? It's just here in this region, and you shift your window there. So I was telling you, our region of interest will be represented by 1, right? So information on the skin, or let's say if you're tracking an object, on that particular object will be represented by 1, and all other information will be represented by 0. And yeah, that's how the mean shift actually works in this particular case. Any questions, guys, so far? Okay, so let's go to the next case where we use represent color distribution with a histogram and use mean shift to find region with most similar distribution of colors. Okay, so how does it work? So you choose a reference model in the current frame, right? And then you choose a feature space and represent the model in the chosen feature space. And that representation will be your, in terms of your color histogram, right? So you specify your one object here. Okay, that we are interested in tracking this object. You define that, and you define the starting point, and then you choose a feature space and represent the model in the feature space. Then you come to the next slide. Let's frame, and start from the position of the model in the current frame, search in the model's neighborhood in the next frame, and find best candidate by minimizing a similarity function, and repeat the same process. So you have some feature in the first frame, you compute the same feature in the next frame, you compute their similarity, and using that similarity, you get, let's say, highest score, best match, and you go to the next frame. I think this one, okay. So let's say in the previous frame, we have histogram, color histogram, and in the next frame, we compute another histogram for the same location or the same model, right? And what do we get? Of course, you will not get exactly similar histogram, not exactly the same histogram in this particular case. It will be somewhat similar to your original model, right? And if you remember from our feature extraction and color histogram lecture, that was also the case when we compared the histogram of the duck image with the histogram of the slightly rotated images of the duck, right? So you'll never find exactly same histogram, but a similar one. And let's say we'll have multiple histograms here, right? Multiple histograms here, let's say, neighborhood as well. Okay? So you match your histograms, and you compare the histograms, and the one that gives you minimum error or the highest score, matching score, you say, okay, that's the one. That's our object of interest. And how do you compute the similarity between the histograms? What measure do you use to measure similarity between the histograms? Again, it's a bit of revision. We discussed some distance measures. Bhattacharya distance, chi-square distance. So they are used for computing the similarity between the histograms. And if you remember from the lecture, we said that, okay, Euclidean distance is not suitable for computing the similarity between histograms. Why was that? because it considers each bin individually. It computes similarity between each bin, and that's not accurate. While other similarity measurement techniques, they take the whole histogram and then measure the similarity. Right? Oh, so with this, we come to an end of this lecture. And just a quick recap: discuss optic flow and motion field tracking, optical flow constraint. We discussed Lucas Kanade